Okay, today I want to talk the simple overview about the step response of series RLC circuit. First, derive the equations that relate the voltage across a resistor, an inductor, and a capacitor in series as the unit step function associated with voltage or current source changes from 0 to 1, or a switch connects a voltage or current source into the circuit. Second, describe the solution to the second order equations when the condition is overdamped, critically damped, and underdamped. Okay, now what is step response of series RLC circuit? First, RLC circuit have two energy storing elements, which are inductor and capacitor. Second, such a circuit gives rise to second order differential equation and hence called second order circuit. Third, the switch will close when T equal to 0 and step voltage of volt gets applied to circuit. This is an example of series RLC network. With a step function voltage source, we have power supply, resistor, inductor, and capacitor. Okay, now I want to discuss about set of solution when T greater than T0. First, similar solution for the natural response and have three different solutions. Second, need calculate the natural angular frequency of the series RLC network and the term alpha to determine which one to use. We must find omega naught equal to 1 divided by square root of LC and alpha equal to R divided by 2L. Okay, this is the example of transient solution when T greater than T0. We have three conditions about this topic. First, overdamped response. Second, critically damped response. And third, underdamped response. Overdamped response will occur when alpha is greater than omega naught. Critically damped response will occur when alpha is equal to omega naught, and underdamped response will occur when alpha is less than omega naught. Steady state solution when T greater than T0. The final condition of the voltage across the capacitor is the steady state solution when Vc equal to Vs. Then this is the complete solution when T greater than T0. We have three conditions about this. We have overdamped response, critically damped response, and underdamped response. Okay, now I want to talk about the other voltage and currents. Once the voltage across the capacitor is known, the following equation for the case where T greater than T0 can be used to find IC equal to C dV over dt, I equal to IC equal to IL equal to IR because we use a series circuit. Then VL equal to L di over dt, and lastly VR equal to IR.
Assalamualaikum and a very good day. My name is Hadirah and I am in charge of explaining the circuit analysis for the series RLC circuit that we have done for our assignment. Here is the circuit for our smoothing circuit. So we have the voltage source of 12 volts, and then we have the resistor of 6 ohms, and then we have the inductor of 1 Henry and a capacitor of 0.04 Farad. To analyze the smoothing circuit that we have done here, we first must know the current for the inductor and the voltage for the capacitor. So when we calculated, we got the inductor current, or the current, because this is a series circuit and it is the same throughout the series circuit, it is 4 ampere. So the current is 4 ampere and the voltage of the capacitor is negative 4 volts. Also, from the results of the calculation, we found out the voltage of the capacitor is the same as the voltage total. In analyzing this circuit, we first have to know the initial condition of both the current and the voltage. So that's the initial condition. T is less than 0, and also the T after the initial conditions. Moving on to the next slide, after we found out the initial condition, or the T less than 0, and the T after the 0 is the same, the current is equals to 4 ampere and the voltage is equals to negative 4 volts, is the same. This is due to the inductor, it can't change abruptly, and the capacitor also, it can't change abruptly, thus making the initial condition and after the initial condition the same. Now it's time for us to calculate the alpha, the omega, and the roots of S1 and S2. This is to determine if this case is overdamped, underdamped, or critically damped. After the calculations, we found out the omega is bigger than the alpha, thus this is an underdamped case. Based on the values of alpha and omega, we chose the equation for voltage Vt and plug in the values since Vt and Vc is the same. Then we know that this is an underdamped case, so we use the equation of Vt is equal to Vs, voltage source, plus A1 cos omega dt plus A2 sine omega dt, exponential negative alpha t. And from the circuit, we can see that the voltage source is 12 volts. And we just plug it in to get the first equation. And then now we find the value of A1 and A2. This can be determined by V naught is equals to 12 plus A1. And we got, this is just Kirchhoff's voltage law, and we got A1 is equals to negative 16. So we just plug it in and we got the answer for that, and then putting it in value of A1, we got the A2, and the complete equation is shown below there. Vc t is equals to 12 minus 16 exponential negative 3t cos 4t plus 13 exponential negative 3t sine 4t volt. So that's the complete equation. Now let's take a look at the simulation that we have done for our smoothing circuit using a simulator called Multisim. We have constructed our circuit in Multisim and we used a few tools in it so that we can better analyze it. One of the tools that we use is an oscilloscope. An oscilloscope is used to determine the waveforms of the circuit. So in an oscilloscope, we can use two channels in it. Channel A, we plugged it in to know the input of the circuit, and channel B, we plugged in to know the output waveform of the circuit. We assume that the output is in the capacitor, so we plugged in there for the output waveforms. Here is how an oscilloscope looks like in a multisim, and channel A is placed to know for us to analyze the input waveforms, and channel B is to determine the output waveform. As you can see, it is plugged into the C or the capacitor so that we can get the output waveforms. Now here is the result of the oscilloscope. So the waveforms shown are both input and output waveform of the circuit. The blue one is the output waveform and the red one is the input waveform. It is constant and regular. About the blue one, it is a little bit irregular because it has gone through the smoothing circuit and it has gone through the smoothing process. From the blue graph, we can see that it had a minor change with the amplitude and the period of the wave to complete its one cycle. This is because the capacitor is discharged and charged, and the output makes the wave become smaller and smoothens from the wave by time. At the end of the waveform, it reaches what we call a steady state. So that means the circuit is completely smoothened, and that means our application is a success. And now I'm gonna pass this to my friend Addrian, and he will continue with the video of the simulation of our smoothing circuit. Thank you very much.
Hello everyone, today I will teach you guys with the RLC simulation circuit in the multisim. Okay, first we construct the circuit. Today I would like to do in series. We take out everything, take out the function generator as our supply, and construct the circuit. Okay, then don't forget to ground the circuit. Come over here. Okay, let's set up our value for every component over here. So I want to use 6 ohm for the resistor, 1 Henry for the inductor, and 40 micro for the capacitor. Okay, and we set up our function generator with the frequency. We use 3 Hz sinusoidal waveform and amplitude around 12. Okay, then what are we going to do is we want to generate the circuit and we get the waveform. To get the waveform, we use the oscilloscope. Put over here. Let's assume that channel A is to the input and channel B to the output. I assume that our output is in capacitor, so that's why I attach the channel B to the capacitor. So I change the color to blue, so it makes easy to differentiate the waveform. Okay, we take the waveform and we generate the circuit. Okay, now we get the reading. So let's change the background of the graph to white, so make it easy to see. Okay, let's pause the waveform for a while. This waveform is quite big, so we can use the scale to see the waveform. Okay, it's now clear. Okay, this is the initial of the waveform and this is the final of the waveform. You can see like this. Okay, what I want to say is, in the initial of the waveform, you can see that the red waveform is the input, as I said before, and the blue waveform is for the output, which is in the capacitor. From this waveform, we can see that the output of the waveform is a little bit make some change. Over here we can see that the amplitude of the waveform decrease and the length for the waveform to complete one cycle also decrease. You can compare with this one. On this part, the waveform becomes smaller and the initial is bigger. You can see the amplitude decrease. Okay, this is because the capacitor, it charge and discharge the output and make the output become smaller and smooth the graph. After it's smooth, the graph achieve its steady state, and the steady state will continue repeatedly until we pause the circuit. That is why we can call this circuit as a smoothing graph, a smoothing circuit, because it smooth the circuit until the end. Okay, that is why we call this as a smoothing circuit. Smoothing circuit usually used in filter as it smooth the graph and the output for every signal. Okay, that's all. Thank you.